Not to be confused with NRL. All right, we figured it out? Yes. How we do that?
How we do what? Eric is going to run things from up there.
So we just finished.
A very short discussion and then we're going to start. Yes, sir. 5:50 we're going to start. So, yeah, and then we have to
What do you got? 7 minutes. So we've lost 15 minutes. No worries. So 15. Wait, so this is. Don't mind that. Just get this done.
This, so. So we discuss it
Let's let Susanna share this go. We're running.
Yes. I just want to
See this. So welcome back, everybody. Just wanted to let you know that we are a little bit late on the schedule. So we will have a shorter discussion before lunch. The group photo is going to be tomorrow, just before lunch. And the Roman calibration discussion is going to be this afternoon at about 4:40, 4:50, whenever we stop. Thank you.
Abby is over there. I have both mics. I can talk twice as fast. Okay, so hope everybody's enjoyed your break. The goodies, including the healthy stuff. Notice the healthy stuff. Okay, so we're going to start with Eric Switzer's presentation. Eric, are you ready?
I'm here. Can you hear me?
Yep. Okay, take it away.
Great. Well, thanks all for improvising on the online arrangement here. So I'll be talking about a characterization of the wide field chromatic response of the wide field instrument. This is just one aspect of the overall flux calibration, but it's one that's important for Roman's cosmology surveys. The motivation here is that differences between the true and the modeled chromatic response can result in systematic chromatic errors. And then tying more specifically to the themes of the conference, the systematic chromatic errors can be driven by differences between the calibrator SEDs and the science SEDs. And generically, the science SEDs will be redshift dependent. So errors in the chromatic response function can turn into redshift dependent photometry errors, and therefore knowledge and control of the chromatic response is essential to studies of cosmic evolution, like the dark energy equation state described this morning. And this parallels Chris's comments from yesterday. The other aspect of a wide field instrument is the calibration sources will appear at different points in the focal plane from the science sources, and those need to be translated. The other translation that occurs is from the bright calibrators to the dimmer science sources, and that's where linearity factors in. And I won't be describing that in this talk, but I hope folks have had a chance to review the poster contributed by Ami. It also includes analysis from Tushara, who's in the meeting. Okay, so the slide shows the overall flow of knowledge going from the element level on the left to flight knowledge on the right. Starting with the filter measurements, the filter witnesses as a function of angle of incidence are measured across the full band, including their out-of-band response. The detector QE is measured per sensor chip and tied to a NIST-calibrated photodiode. That flows into system level tests in thermal vacuum or TVAC that use a monochromatic light source. There are two varieties of the test. One sweeps over the filter edge to provide additional information about the coating model across the flight optical surfaces. And that's one area I'm going to focus on for the response here. The other is a sweep over the full wide field range that supplements the QE measurements by providing an inter-sensor chip tie-in. So those get combined with the flight mirror, the telescope mirror characterization to give a data cube of the chromatic response over the field. That ground data cube is a prior for flight calibration to yield the final flight chromatic response model. And one of the key aspects that you learn from the flight calibration is the overall throughput. And at the bottom here, I cite a paper describing more information about the systematic chromatic error. This slide shows the element wheel assembly and all of its filters. I'll be focusing on the imaging filters labeled with F and also W146. For more information about the spectroscopic elements, the GRISM and the PRISM, please see Evan's poster in the meeting here. On the right are the passbands for each of the imaging channels. Okay, so this slide shows pupil imaging data acquired by Evan that characterizes the transmission of the F106 spare red edge. And what's shown here is data from essentially a mock telescope where instead of having a focal plane, there's a camera that looks back at the pupil, and then monochromatic light can be swept through the edge wavelength, and you can ask at what wavelength does each part of the optic pass through its 50% transmission point. So that's what's shown in the plot. So there are two key pieces of physics that need to be incorporated in the wide field chromatic response model. The first of those that you see is that as the optic is rotated from 0 to 5 to 10 degrees, the edge blue shifts, and this is a well-known effect in interference filters. And in this case, it's well described by an effective monolayer model shown in the bottom right. The other aspect here, you can see looking across the surface of the filter, and that is that there are roughly parabolic variations in the edge wavelength across the surface of the filter. These are thought to be due to deposition of the filter coating on a slightly curved optic. And this is well described in the same monolayer model by deviations in the effective thickness at the level of 0.3%. So both of these pieces of physics need to be incorporated in the planning and analysis for the system level test. So that's shown in the bottom left. And here there are 4 fibers that illuminate a ground glass diffuser that provides a full field of illumination. The fibers are fed by a laser line tunable filter that is illuminated by a supercontinuum light source. And then wavelength knowledge is provided on site by optical spectrum analyzers tied to line lamp sources. So the figure on the right shows the stack up of considerations that need to be included in the analysis. Starting at the top is an image of the diffuser where you can see the illumination spots of the 4 fibers. Then from a given point in the field, you'll see through the pupil mask to a region of that diffuser. So that's the next level down. And at each point in the field, there's also a range of angles of incidence across the filter. And then finally, there's the variation of the coating itself across the optic. So at each point in the focal plane, the flat field is the integral of all these contributions. And I'll unpack each of these and talk about how they're determined. So One of the outcomes of the variation across the filter surface is that the uniform illumination in flight results in a broadening of the edge. So here on the left, the black shows the witness measurement, and then the colored lines show the diffuser data and a model of those data that I'll describe. And you can see that the edge is a little bit broader. And then also as you go from the center of the field to the edge of the field, the edge shifts shortwave. The other aspect of having the variations across the coding is that the variations in the diffuser illumination that weights the coding in the test need to be considered in detail. And I'll talk about how that's handled in a slide, upcoming slide. So the figure on the right shows the range of angles of incidence that drive this angle of incidence dependent blue shift. And these range from up to roughly 13 degrees. So this shows the red edge wavelength across the field running roughly from 977 to 983 nanometers. The principle of the measurement is that with monochromatic light passing through in a flat field of illumination, the center of the field for this filter will be in transmission. So you can see at 980 nanometers, the center field is still well within its transmission range. And then the edge of the field is in blocking. So you can see that these are the TVAC data on the right, that the center of the going from the center to the edge, you go from transmission to blocking. As you move further redward out the filter edge, the center of the field drops to 20% transmission, and then the rest of the field drops into a harder blocking region. The measurement proceeds by gathering a data cube of these mosaics as a function of wavelength. And you can ask at what point those pass through their 50% point, and that's the pattern retrieved on the left that shows the edge wavelength, the 50% edge across the field. Oh no, this is a relative measurement, and the throughput is derived from the element level measurements that have a filter, an optic in and an optic out. So that's from the ground, and then in flight, that will be superseded by the calibration sources.
Eric, you have 5 minutes.
Okay, thank you. So this summarizes the filter edges, blue and red for each of the filters. The vertical axis is the wavelength, so you can see the edge, and then the the horizontal axis is the angle of incidence, roughly the position in the field. You can see that each of the edges blue shift as you go across to the outer edge. The numbers on the top show the requirement range for the wavelengths, and each of the filters land easily within those requirements. Okay, so I mentioned that a key aspect of this is characterizing the illumination of the pupil by the diffuser. So for that, there was a dedicated pupil imaging campaign with a camera as a surrogate to the wide field focal plane that looks back at the diffuser through the pupil and its illumination pattern. That's at 18 field points, and then the full field of illumination is modeled using ray tracing and a model of scattering through the diffuser. So that's shown in this figure, where you can see the illumination pattern as a function of field position. So the flip side of this this weighting of the pupil is that the flat field contains subaperture information. So the analysis proceeds by a forward model that retrieves both the field dependence and the pupil space dependence to retrieve the coding variation. So this shows for FO87 blue and red. On the top is the field, and then the bottom is the coding across the surface that's retrieved. You can then ask how well that model, which is based on the field-dependent diffuser illumination and the retrieved coating across the surface, how well that describes the actual optic. And this slide shows the residual in the edge wavelength determination, again for FO87. And this is bracketed by, the whole range here is from roughly plus or minus 0.03%. In addition to the model versus the data, there's also the absolute wavelength knowledge that ranges from 0.004% to 0.03%. And these are all in wavelength rather than in flux. So all the other bands land within a 0.06% wavelength knowledge. And I'd be happy to talk about the structure that is there and ongoing work to push below this level. But translating this into photometry, this lands within a 5 millimag chromatic photometry budget. Okay, as a cross-check of the forward model for the variation across the surface, we also performed focus diverse phase retrieval. So this retrieves the amplitude across the surface, and that's as a proxy for the transmission as a function of wavelength. You can see on the bottom left, the flat field and the FDPR showed the same consistent pattern of variation across the surface. Okay, so to summarize, control and knowledge of chromatic error is essential to surveys of cosmic evolution, supernovae, photoz's, also things like the weak lensing chromatic PSF. The wide field provides unique considerations for the range of angle of incidence across the optic. So for the system level characterization, we retrieve both the pupil dependence and the field-dependent transmission with a cross-check. These wide field effects need to be incorporated in the survey planning and analysis. I think an interesting area for ongoing work will be thinking of the ground characterization as a prior and then using flight measurements, such as a range of stellar colors over the field of view to test the chromatic response. Actually, in talking to Misha, it sounds like that will be a topic of a future talk, but I'm happy to take questions, and please reach out if you're interested to collaborate.
Right on time. So we have time for some questions. Eli?
Thanks. This was a very interesting talk. What you said a slide or two ago, you said within the 5 millimag requirements, the impact, was that before or after correction? So are you just like eating this, or are you correcting for it? And if so, how does the pipeline correct for the chromatic effects over the field of view?
This would be after correction. So the treatment of the variation across the field could be science dependent based on the survey, but generally through the flat field. But one area of ongoing work is to understand at what level of the pipeline the field dependence needs to be incorporated. I don't know if Stefano is here or would like to comment there also.
Yes, Stefano has his hand up.
Yes, that's a very good question. Unfortunately, I don't think it has a good answer. In principle, you can think of the pipeline as being able to correct for your for your flat field at one particular SCD only, which is the SCD for which you have done the flat field correction. Anything beyond that depends on the individual source SCD. Therefore, it cannot be done as a part of the pipeline. It has to be done post-processing in some way by taking into account what the spectral distribution of a source is, and then using that information and its location in the focal plane to do that correction. So the information that Eric is presenting is critical to doing that correction, but it's not something you can apply routinely part of the pipeline, at least not to the extent that I know. If someone has a brilliant idea to do it.
We should chat that.
Okay, thank you.
Okay, we have time for a couple more questions. Are there any questions online? Okay. Sean, you think those mics?
Really great talk, Eric. You didn't talk a lot about the 213 filter and the red edge of that. Do you have any, I know it's hard to calibrate. Do you have any concerns about the wavelength variation on that compared to everything else?
Yeah, that's a great question. So F213 was added later than the other filters. So from a requirements perspective is a best effort. So we do have the blue edge and the witness measurements, and the variations across the surface for coatings that are on the same side of the optic appear to be consistent between side 1 and 2, or between the blue and the red edge. So we can take what we learned from the blue edge and translate to the red edge, but that's one where I think use will require some additional consideration of the chromatic photometry.
Okay, so let's thank Eric. And next we have Meredith Durbin on class calibrating HST at 2 minutes.
The notes, sorry. There we go. Sorry, folks, stand by. Okay, thank you. All right, hello everyone, thank you for your patience. My name is Meredith Durbin. I'm a postdoc at UC, and I'm going to be talking about some of my thesis work that I did mostly with Rachel Beaton, who is out of town this week, but I'm sure many of you know. So there's been a lot of interest recently in using various types of cool evolved giants as distance indicators because they're some of the brightest stars around in the near infrared, and they can also be found in galaxies without recent star formation, unlike classical Cepheids. The one that is historically best established in the literature and the one that initially motivated this work is the tip of the red giant branch, or TRGB. And lately, there's also been a lot of interest in using the period luminosity relations of Mira variables and semi-regular variables, and also the luminosity function of carbon stars, become known as the JAGB. And I think that these all have a ton of potential, and that they also pose some unique challenges when it comes to fundamental calibration, especially in terms of cross-calibrating between facilities. So As it happens, all of the things that make building this kind of cross-calibration sample hard are kind of turned up for cool giants. The first thing you want is, of course, low reddening. Well, the nearest giant stars are statistically more distant and therefore more reddened than main sequence stars. You also want accurate geometric distances, which is especially difficult for galactic AGB stars because of the motion of large convective cells on their surfaces that can affect the photocenter positions and therefore parallaxes. And not only do you want to be able to measure at least some of them with good precision from multiple facilities, you really want to be able to get a relatively large sample because these are statistical distance indicators that work on the population level. And this gets really expensive really quickly. So in lieu of actually doing that, we can turn to the old workaround of deriving transformations between filters from synthetic photometry. So even putting aside whether we can ever really know a bandpass, filter transformations get tricky for AGB stars in the near IR in particular, because you have these really wild SED properties thanks to molecular absorption. In the O-rich ones, you have these deep water features that bracket the 1.6 micron opacity minimum. And in C-rich ones, you have just all sorts of carbon species all over the place doing whatever. And the RGB and early AGB, or non-thermally pulsing AGB, look pretty well behaved in comparison, but even there, the spectra are not necessarily smooth. And when you care about 1% broadband photometry in multiple photometric systems, this can make your life even more difficult than it already is, because the exact way that wide bandpasses sample these spectral features can vary a lot between instruments. And I'm illustrating this here with the F110 and F160 bands on WIFC3IR and the 2MASS JHKS bands for comparison, which are the ones that I'll be focusing on for most of this talk. And the scatter points on each spectrum are the integrated flux densities in those bands at their respective effective wavelengths. And the more pronounced the spectral features get, the more the integrated fluxes diverge between bands that are intended to otherwise be roughly analogous to each other. And of course, there's a lot more complex physics going on with these guys than just molecules in the atmospheres. They're highly convective and usually not spherically symmetric. They're losing mass and producing these circumstellar dust shells. They have long period and often multi-periodic variability in amplitudes anywhere from about 1/10 of the meg for the upper RGB to like several magnitudes for Myras. And all of which is to say, these are kind of the opposite of standard stars. And even though there's been a lot of really great progress in modeling them recently, what you really want to use if you're going to do synthetic photometry is empirical spectral libraries. So now that I have spent all of this time talking about cool giants, those were the impetus for doing this work. But as I started looking into available spectral libraries with near IR coverage, I said, you know, we really can't get away with leaving CalSpec out, even though it doesn't include a lot of giants because it's such a fundamental benchmark. And from there I went, well, there's no reason to not just do the entire HR diagram while we're at it. So we ended up combining 4 spectral libraries to get a sample of around 1,000 stars with continuous spectral coverage, with the spectral continuum preserved between about 0.7 and 2.5 microns. And to my knowledge, there's really only one other library that has continuous coverage in this wavelength range, and that one focuses mostly on brown dwarfs. And I would love to be wrong about that, so if anybody knows of any that I missed, please do point that out. And I want to highlight the X-Shooter library in particular because it's really what made this project work. XSL was designed to bridge the near UV through near IR for population synthesis applications. So they sampled nearly the full HR diagram pretty thoroughly, and for the AGB stars, they observed a number of them over multiple phase points in their variability cycles so that they could average them out in an integrated population. And X-Shooter is able to take simultaneous spectra with its 3 wavelength arms, so they were able to accurately capture the effects of variability over the full spectrum simultaneously. So once I had this multi-library sample, I also assembled the best fit distances, line of sight reddenings, and fundamental parameters from the literature and from archives, as much as I could find them. And even though we're not trying to do anything involving absolute magnitudes here, we do want to de-redden the spectra for relative color calibration. as fraught as that is. So we need distances to estimate their line of sight reddenings from 3D maps. This is just showing the stellar parameter space that we cover with the sample. It's about 3 Dexton metallicity from -2.5 to 0.5, although I wasn't able to gather specific abundance information for most of these. And we have effective temperatures from about 2,500 to 60,000 Kelvin. And we range about 8 Dexton surface gravity. So there's just like a lot of stars here. And for reddening, I compared values from 5 different 3D maps and also 3 different star-by-star fitting techniques. And please don't try to read this corner plot. But the upshot is that they're all mildly different, but not at a level that actually really mattered when it came to our final results, because we ended up rejecting a lot of the high reddening ones anyway. And the one we ended up going with is from Lalemant et al. 2022, which is a 3D map based on Gaia EDR3 that had the most complete 3D all-sky coverage out of the ones that we looked at. And that was updated by Virgili et al. 2022, I hope I said those names right, to improve the results for cool giant star sightlines. So that was really important for our application. And when I showed this plot to Rachel, her response was, I'm going to start the journal of comparing things that should agree, but kind of don't, but also should they, and just pick one, which I think is a really beautiful way of summing up a lot of what we do here. So some details about the synthetic photometry procedures that I did. I think this is maybe like the only audience who really cares about that. So I largely followed the example of the Gaia DR3 synthetic photometry catalog in treating the spectra and normalized bandpass curves as basis vectors, so that the integrated fluxes and their covariances could be treated as dot products. And that simplified the uncertainty propagation and sped up the computation considerably relative to the implementation in the SynFOT code package. And I did check things against SynFOT. It all comes out to within numerical precision. And also, please nobody ask me about units. I will confuse myself if I have to talk about those on the fly. And for the wavelength grid, because everything has to be sampled on the same wavelength grid if you do it this way, I chose the one on which the HSC flux covariance is defined on CalSpec, so that I could include that as kind of a baseline systematic term in all of the flux covariances. And I also included uncertainties on the line of sight reddenings in the dereddened spectra. And for the ground-based spectra, I filled in the wavelength regions that were dominated by tellurics by just convolving over them, which tends to work fine for most of the smooth spectra, but I wasn't entirely happy with it for the ones with these sharp molecular features. But also, there's only so much that anyone could really do about that. And finally, I set 0 points with the latest CalSpec Vega spectrum, and that was all the absolute calibration I really did. So here is what the final 2-mass color magnitude and color diagrams of the full synthetic photometry sample look like, where the dark blue points are spectra without any sort of flags. The orange and pink ones are CalSpec stars without HSC spectral coverage in some or all of the near IR. And the green and red points are X-shooter spectra with wavelength-dependent flux loss or other calibration factors that might affect their continua. And here is the real 2-mass photometry for comparison, where the dark blue points are the highest photometric quality. And overall, I have to say that considering not all of these libraries are absolutely flux, I think it looks pretty good. And the dominant term when you compare the colors directly is actually the 2-mass photometric errors. So now that we have sanity checked our synthetic magnitudes, we want to use them to construct color-dependent filter transformations that cover as much stellar population parameter space as we reasonably can, but we also want to minimize the scatter. So first, we reject stars with the high uncertainties on synthetic magnitudes, which are mostly from reddening. And you can see that, as I was saying earlier, this really disproportionately affects stars that are on the upper giant branches. And I also rejected spectra with any of the flags from the previous slide. And finally, try as I might, I found that effective temperatures below about 3,500 Kelvin were really the cutoff, below which there's just like not any one-to-one relationship between filters, which we'll look at a bit more later. And This is pretty similar to what the Euclid folks did for their filter transformations, where they had one set of transformations for O through K stars and another for MLT types. So for the well-behaved quote-unquote normal stars, the overall dependence of the HST versus 2-mass filter differences follows a pretty tight relationship with color. The rows here are F110 minus J, F125 minus J, and F160 minus J. And the columns are 2-mass J minus KS and J minus H. And in pretty much all cases, the RMS scatter around the fitted relations is in the vicinity of 100th of a magnitude, which is like, I mean, we're not doing things on the millimag scale here quite yet, but like for what this is, I think it's pretty good. And I fit all the transformations as piecewise linear relations that are conditioned to be continuous, such that the starting point of each segment is the sum of all of the previous segments. And I chose to do it this way because in some cases, there are these really sharp slope changes that aren't well fit by polynomial terms. For example, in the upper left plot of 110 minus J versus J minus KS, you can see the steeper slope that's caused by the Paschen jump in A-type stars, which is bracketed by the 2 dotted lines, which show the breakpoints of the different segments. And even for the filters that don't have these steep slope changes, they're about equally well fit by piecewise functions as by low order polynomials. And so if we take these relations and we extend them, extrapolate them to the same AGB stars that we rejected in this fitting process, you can really see where things kind of start to go off the rails. So the blue stars here are the carbon-rich AGB, and the orange ones are oxygen-rich. And I'm also showing first descent red giants, our Lyrae variables, and classical Cepheids for comparison. And not only do the AGB stars scatter way off of the nominal transformations, but they don't even really do so in a consistent manner. And you could make the case for a linear relationship for the carbon stars in F110 minus J, but then the others, really, everything kind of goes out the window. And the lines connecting some of the points in these plots are showing the same stars observed at different phase points in their variability. So what I think is going on here is the relative strength of the molecular features is changing as they change temperature in the pulsation cycle. So like even within a single star, they're not consistent in how they scatter off of the nominal color relations. And like these residuals are all on the 10th of a mag level instead of a 100th of a mag level. And I also recently extended this project to sort of just do the same thing for some bands on NearCam, Euclid, and Roman, as well as a couple bluer ground-based bands and HST bands. And the situation is like pretty much the same across the board. These violin plots are the average residuals by stellar type for 105 unique combinations of all of the bands shown here. And I am not trying to say that these should be taken as like absolute systematics on like AGB-based distances or anything, but it seems like we have to find another way to cross-calibrate them than with simple color term transformations. And like it's unclear to me at this time how to do that in a way that is both principled and not incredibly expensive. So any ideas on that would be really welcome. And finally, I want to switch gears here a little bit and talk about a program Rachel and I have been working on, along with a few other folks, to actually do an empirical cross-calibration of the tip of the red giant branch between WIF-C3IR and ground-based JHKS. And the Magellanic Clouds are really the only place that you could reasonably do this. And even here, it's a challenge because you're right around the saturation limit for WIF-C3IR. So we had this multi-cycle pure parallel in with HST that took about 70 odd pointings in both Magellanic Clouds, which I plotted here. And this was a parallel with the Ulysses program. And for these, we got with C3IR imaging and Prism spectra. And then we followed them up with imaging from the 4-star camera on the 6-meter Bada telescope at Las Campanas. And all of the data from that was reduced by our collaborator, Andy Monson, who, as it happens, also built the instrument. And one cool thing about 4-star is that in addition to JHKS, it has these custom medium bands that were developed for the Z-Forge Galaxy Survey to measure photometric redshifts. And these are also really good at separating out the different types of AGB stars because they sample the molecular features very well in kind of a similar way to what Martha Boyer has done with medium bands on HST and now also with JWST. And the tricky part with those is that you can't just calibrate them to 2-mass like you can with the broadbands. So we worked with a summer student this year, Maya Seagraves, who did some really, really excellent work on calibrating them semi-empirically with SED fitting. And she'll have a poster on that at AAS this year, so be sure and look out for that. And so aside from Maya's work, this project has kind of been on pause since I graduated for a number of reasons. But just to show you where things stand and why we had to get 4-star data instead of using 2-mass directly, these are the color magnitude diagrams of everything we've got so far. We're just still short a few 4-star fields because a lot of the HST data came in right towards the end of the program, which also happened to be a few weeks before my thesis was due. So that made that summer really fun. And because it was a pure parallel, we didn't actually know the field locations in advance, so we couldn't take the 4-star data ahead of time. And anyway, that's just how it shakes out. And you can see that the HST and 4-star CMDs are pretty comparable overall, whereas in 2-mass, you hit the limiting magnitude right about at the red clump, which means that you don't have great signal noise at the TRGB. So that's kind of where that is. Hopefully we will be wrapping it up soon. As far as future work goes, I'm planning to do a few more things with the synthetic photometry in future. One thing is to try it out on some state-of-the-art models, such as the new Bose synthetic atmospheres, which I'm looking forward to hearing more about later this week. And I also want to take a look at integrated light at some point, which I think could be really interesting for surface brightness fluctuations. And I also think it would be really cool to sort of test out the chromatic field dependence we just heard about on some of these AGB stars. And looking further ahead, I want to join the small chorus of people here who are advocating for cool giants to be sort of considered as standards. And like obviously maybe not like some of the weirder AGB stars, but I would love to see a dedicated spectrophotometric reference library for them. And I was really excited to hear about SphereX, and I think it might have a lot of potential in this area for galactic stars. I am actually just about done 5 minutes early, so I will leave my summary slide up and take questions.
Thank you, Meredith. Questions?
Yeah. That's fine. Mike Gordon from BAE Systems. It's really interesting using evolved stars as calibration targets. As you mentioned, the fact that they're bright makes them quite appealing, but I'm a little bit concerned about some of the IR excess issues that I know George Ricci showed, I think on the first day, that some close to maybe Vega, and it's even worse in RGB stars, will have multiple like cool components from like a pseudophotosphere for RGB stars or other winds, pH contamination even as well. So I wonder if you thought about like how applicable this would be for wavelengths even slightly longer than 2-mass, because I know you can see some contamination even in the IRAC, 3.6 and 4.5 micron bands from RGB winds.
Mm-hmm. Yeah, to be honest, I had not thought about that, but a couple of these spectral libraries do actually go out to those wavelengths. I don't know how good the data is out there from the ground, but IRTF and EIRTF actually do go out there. So that could certainly be something that would be interesting to look at in future. Thank you for bringing that up.
I can hear you.
Okay, so in the spirit of what we heard yesterday about standard software, what package do you use to do all this spectral analysis, or you know what I mean, synthetic photometry? Is it you rolled out your own, or did you use Synfold? Or
So I started out using Synfode, and then like the thing that was difficult with Synfode was doing the uncertainty propagation. So I ended up actually just kind of re-implementing a lot of what's already in Synfode with some simplifying assumptions and like some vectorized code, basically. So like it was like Synfode, but like very slightly to the left is mostly what I used.
Questions? There's one in the back. So we'll go 1, 2, 3.
Excuse me.
Skip you.
So the extruder uses shell gratings, which are to rid of the shape place. And do you know if there is any star in common with CalSpec, and have you an idea of how well do this in spectrophotometry from computer?
Yes, so there are a couple stars in common with CalSpec in the extruder library. I did look at them. I no longer have those plots on hand, unfortunately. But as far as I could tell, like at least over the wavelength range that we're concerned with here, they did largely agree with CalSpec. I couldn't give you a number off the top of my head, but I like in the broadband photometry, like we're looking at sort of few percent errors from the non-CalSpec libraries anyway. So like it was certainly good enough for our purposes here.
Anyone?
So I want to help with the question you got about synthetic photometry past 2 microns. It works great. But the whole calibration that I reported on depended on that to a large extent. Now, if the star has an infrared excess, of course, you don't get it in the synthetic photometry. The one caution is the W3 filter is a mess. It's very broad and very complex, and I think I might not trust synthetic photometry with a filter like that.
Thank you.
Are there any questions online?
I don't see any.
You have time for one more question. Jamie?
So you sort of started to allude to this, but as people are starting to think about using these as distance indicators, how worried are you about those uncertainties and kind of the AGB stars making that just not feasible? Like where are we on that space?
I mean, I think that like the way that people have been doing it so far is they've been like basically just using JWST and using NGC 4258 as the geometric calibrator. So that kind of like bypasses this whole issue really. But like I do think that if we want to try and tie these back to like say like the Gaia parallax scale, like that's kind of where I worry. And like I don't know that it's like not doable, but like I think it will take a lot of coordination and like just a lot of effort to do so. That's my take.
All right, well, let's thank Meredith. Okay, our next speaker is Michael Wiley on the absolute sky seen through the lens of calibration spectra. Let's see if I've actually learned how to do this. Okay. Second. All right, who's your the on switch?
Okay, thank you.
Cleverly hidden. Wait, it's not sharing.
That's sharing.
Oh. I don't know how this works.
Excuse me.
Ideals. I looked at the I mean, like this. Yeah.
Okay, thank you. Okay, hello. I would like to talk about two particular problems with calibration. And my presentation will be quite on the theoretical side, I'm afraid. There will be equations, a lot of them, no way around that. But the next presentation will be more practical and illustrate nicely, I think, what I'm talking about in this case. And I also think that this presentation and the next one nicely connect to what we have already mentioned yesterday in the discussion round, because the first problem I want to talk about is actually the problem of passband calibration or passband reconstruction. And, well, I can point here. Well, starting with the equations, the first one is just a very basic, plain and fundamental description of a photometric measurement. We have some photon flux if we have a photon counting instrument, as we usually do. And this is related to the spectral photon distribution by just multiplying it with a filter passband and integrating over all wavelengths of relevance in this case. And the calibration problem in this case is just assume we have, keeping it abstract, a set of M calibration spectra with a well-known spectral photon distribution. And we have the measured photon fluxes in the filter passband in this case. We can assume this to be given, and the problem is finding the passband in this case. And the second problem I would like to mention may at first look appear very different, but technically it's very much the same. It's a problem of spectrophotometric calibration of spectra. The fundamental formulation is very similar in this case, just that we don't have a scalar on the left-hand side of this equation, but a function of some focal plane position or coordinate, maybe in millimeters with respect to a reference point in the focal plane, or the CCD pixel position or something like this. And this is linked to the spectral photon distribution, not only by the response curve of the instrument, but also by a dispersed line spread function in this case. And here we have two different kind of calibration problems that can occur. First one, we can assume that we have, again, a set of M calibration stars to be given and the observed spectra to be given. And we have to find our instrument to know what our instrument is doing. And once we have found our instrument, we have to calibrate a particular spectrum, which is we have the instrument given and the observed spectrum given. We have to find this one here. In this case, you might not agree fully with the formulation of the problem, because usually one does it in a different way, which are called here high-resolution spectra with high in exclamation marks. One just takes a focal plane coordinate and transforms it into a wavelength with help of a lamp spectrum, and then just simply ignores the LSF effect, which technically means we approach the LSF as a delta distribution. If you plug this into this integral, the integral just disappears, and it gives a nice, simple expression for the observed spectrum as a function of wavelengths. It's just linked to the absolute known spectral photon distribution by the multiplication with the passband, and then you just have to divide the observed spectrum either by the known catalog spectrum or by the response curve to do the instrument or the spectral calibration. This works very nicely in most of the cases, but there are, not very often, but there are cases where the effect of the LSF cannot be neglected like this. To give just some example where this can be the case, I show here the response curve of a Gaia low-resolution spectrophotometer. This figure shows a lot, so just focus on the shaded region, which is actually the response curve of this instrument, and the red line, which is just this approximation here, dividing an observed spectrum by a known spectral photon distribution. And this gives a very nice approximation of the two response curve. But as you go to longer wavelengths, the LSF of the instrument becomes wider, and at some point you hit a wavelength cutoff filter, which has a very abrupt drop in the response curve over here. And in this region, the approximation of the response curve is really bad. It doesn't work anymore like this. So when I talk about high and low resolution spectra here, I don't mean some kind of absolute resolving power of the instrument, but just can the LSF effect be ignored in the calibration or not? And this depends on the scale over which the response of the instrument changes in respect to the width of the LSF. And in cases like this, where this change is very abrupt in the response, one still has to stick to the full integral equation one sees on the top of it. So we have two very much related problems mathematically, the passband reconstruction and the low resolution spectroscopy calibration, which has the same kind of integral equation. This equation is important enough to have a name of its own. It's a Fredholm equation of the first kind. And we can consider the passband reconstruction just as a simplification. So it becomes independent of one of the two variables in this equation. So these are mathematically very similar problems. So we can think about how to solve these problems in principle. And when we know how to solve such problems in principle, we can ask ourselves, how should the set of calibration spectra we have available to solve this problem ideally look like? The technical approach to get here is, well, in some sense, very straightforward. First, we just have to assume that all functions we are concerned with are square integrable, which just means that the integral over the square of the function is finite. This is a very relaxed assumption. Usually, our functions satisfy much more stringent requirements. But if you go for the square integrability, we know that these functions form a vector space, not just some vector space, but a vector space that comes with an inner product. The inner product of two vectors, so two square integrable functions, is just the integral of the product of these two functions. And if one has a vector space that has an inner product, the inner product gives rise to such very familiar concepts, just like length or distance or orthogonality. Just to illustrate this with some familiar vectors, so just think of a vector in three-dimensional space. The length of this vector is just the square root of the inner product, the normal scalar product of vectors with itself. In three-dimensional space, it would be the square root of x squared plus y squared plus z squared, which is just the Euclidean length of this vector. And we just have the same expression if you just put in the inner product of the vector space of square integrable functions here. And the same for orthogonality. Two vectors in three-dimensional space are orthogonal if the scalar product between is 0. And so some square integrable functions are orthogonal with each other if the inner product between them is 0. This structural relationship is very clear and straightforward, which means we can use very familiar concepts of vector calculus to approach our problem of integral integrations we have here. If we do this first for the passband reconstruction problem, first we construct an orthonormal basis with our basis functions of our calibration sources. If we have a set of m vectors in three-dimensional space, for example, we can immediately compute an orthogonal basis from them. Just the textbooks would say you do some Gram-Schmidt orthogonalization. We do the same with our functions, just not with Gram-Schmidt orthogonalization, but probably some kind of functional principal component analysis would be the way to do it. Then we have n basis functions, so the dimensionality is n, which is a number somewhere between 1 and the number of calibration spectra we have. We develop all our spectra in this orthonormal basis and just plug this into the equation we had before and change the order of integration and summation. I'm going through it very quickly, I know, sorry. But then we will find an expression like this. So the observed flux for the east source is just the sum of all basis functions, so coefficients of this source. And then, well, this is an inner product again. It's an inner product between the passband and the basis functions we have here. And if we have an orthonormal basis, the scalar product of a vector with one of the basis functions is just a coefficient in the development in this basis. So this expression here is just the coefficients describing the response curve in the basis spanned by the calibration sources. And this already looks like a vector matrix operation in here. And if we write it for all of the calibration spectra we have available, it indeed becomes just a linear equation we have to solve. An m vector of observed fluxes is related to the n vectors describing the passband in the basis of the calibration spectra and linked by a matrix which has all the coefficients for all the calibration spectra in here. And this we can immediately solve for the vector p describing the passband. And we have a solution for the passband, which is then just developing the passband in these coefficients with the basis we have. I put here some index parallel and say it's a solution for the passband, but not the solution for the passband, because what happens if the passband has a component in its development that is not included in the basis we have from the basis from the calibration spectra, which might well happen because there is no physical relationship between the stellar spectrum and the passband. So it means in effect we have still some freedom, namely the freedom to add to our solution another part describing the physical passband, which is in mathematical sense orthogonal to the solution we have found before, which means that this component is orthogonal to all of the calibration spectra we have. And well, it sounds like a mathematical detail, but this is actually of quite significance in practice, because what happens if you now do synthetic photometry with a source which is not fully described by the basis functions we have in our calibration sources, but has some other component orthogonal, then it will depend on this orthogonal component of the passband that we add, in which we cannot constrain from our calibration sources, but we just have to guess it in some way. And this might make, in this case, synthetic photometry very prone to systematic errors. To give an example, I show here an example for the Hipparcos passband calibrated with 206 NGSL spectra. I'm not saying that this is the best way to do it, but it will do for the sake of the argument here. And in this figure here on this side, you see this red curve, which is the parallel component of the passband, the component that is uniquely determined by the calibration spectra used. And in this case, I produced one possible orthogonal component. This is this blue curve here. And if you add the two, you get a nice smooth passband, which should be physically, from a physical point of view, realistic. Okay. And well, the residuals are nice. You see them here in color and in magnitude without trend. And we know mathematically that these are the smallest residuals you can get. But you can add some other passband, some other orthogonal component as well if you want to. This is what you see on the other side of this plot. The curve A here is the same as on this side, but the curve B has just another orthogonal component, slightly different added. So you get a slightly different overall passband in here. And the blue curve C has an orthogonal component added to it that deliberately was made in such a way that the passband looks grotesquely different. But if you look at the residuals again, all three passbands will produce residuals of the calibration sources, even in the fine detail of the noise. These three solutions are completely indistinguishable from the set of calibration sources. And you might say, okay, this grotesque blue curve you can reject from your a priori knowledge, but the difference between the curves A and B, the black and the blue one, might still be within your tolerances you know from your passband a priori. And if you now apply this to a set of sources, you can get into troubles. This plot here are just taking some spectra from stars. This is a Pickles library of spectra of different spectral types. This is the difference between the solution A and the solution B and C. And the color coding is just an indicator for how much the source depends on the orthogonal unconstrained component of the passband. 0 means, in this case, 0 degrees, the source is entirely linear combination of the calibration spectra, and 90 degrees, where it means it's perfectly orthogonal and only depends on the guessed component. And for the red curve, you get some, but you get very nice agreement for sources which are linear combinations, of course, but for the red curve is a slightly different orthogonal component. You get some systematic deviations, particularly for very red sources, which have a strong orthogonal component. In this case, the systematic difference is something like 50 to 60 millimach, which sounds small, but when we have some catalogs with a photometric accuracy and a random error of about 5 millimax, it's still quite a lot, actually. And if you go to this grotesque curve, well, you get grotesque values, although calibration sources all look perfectly fine. For the lower resolution spectroscopy problem, the situation is very similar. The only difference is that we have to produce two orthogonal bases from our spectra, for the internal and the external one, and we link them by a matrix describing the instrument in this case. The elements of this matrix are then just the observations of the basis functions projected on the basis of the observed spectra. And we can just solve this problem again for the instrument matrix if you do the instrument calibration, or for some matrix C of the coefficients we want to calibrate a spectrum. The point is, again, this transformation between the observed spectra and the spectrophoton distributions is limited in the knowledge to the basis band by the calibration spectra. And everything outside this range needs to be guessed, so this calibration becomes very prone to systematic errors again. I'm coming to the conclusions. There are quite a lot, actually, from this presentation. First of all, yes, if you have some high-resolution spectra, you can do a calibration very easily by just having one nice calibration spectrum, say a smooth, easy-to-model white dwarf spectrum. You just do some divisions and your job is done. But if you go to calibration problems like the passband reconstruction or photometric calibration, spectrophotometric calibrations, where you cannot ignore the LSF, you have completely different requirements. Well, first of all, different shapes of the spectra for the calibration are needed. And we can be more precise here. It's not just different spectra. We need different linearly independent components in the spectra. So it's a problem of the dimensionality of the calibration spectra. Adding a different spectrum, which still is a linear component, a combination of the spectra we already have, will not result in any improvement in this sense of the calibration. Well, for the part that is constrained, there is a unique solution. We can do a chi-square solution of a linear problem, which has a unique minimum, and you have even an error that tells you how far you're allowed to go away from your optimal solution, which is all you can expect from any kind of measurement. And this part is just what constrains your calibration. Well, for the other part, it's unconstrained by your calibration sources. You have to make a guess on your initial a priori knowledge of the passbands or so. But this means that the problem for these sources can become very prone to systematic errors. It can become serious in some cases. So ideally, what you would like to have is a set of calibration sources which allows you to represent your passband or your instrument perfectly as a linear combination. Then there would be no orthogonal component you have to estimate in some way. Or at least to have a possibility to represent all the spectra you're scientifically interested in as a linear combination of your calibration sources. Then the orthogonal component doesn't matter anymore, which is, of course, wishful thinking. You will never get this, but you should try to get close to it at least. So the basic message is that a variety in the spectral calibration spectra is mandatory, and the more linearly independent component you have in there, so the higher the dimensionality of the space spanned by your calibration spectra, the better your calibration will in the end come in such problems. And that's the end.
Questions?
You said you want a principal component analysis. Now, I'm curious, what if you had emission lines on your spectrum? What would that do to your kind of analysis? Because emission lines can be anywhere.
Yeah, well, depending on where they are and how frequent they are in your set of calibration sources, they will pop up somewhere in the principal components. And if they're just a few lines, they will move very far away in the lower order principal components. You might not get them anymore, which is related to the other problem. Where do you make your cut in practice? What is your two-dimensionality of the kind of set? On the other hand, if you would have very many emission lines in your spectrum distributed everywhere, you would probably get a very nice basis, because then they will all be in the leading ones, and you can build up very nicely a spectrum with emission lines, passband with emission lines, if you have enough of them. So I would be very happy to have a set of calibrators which are full of emission lines everywhere, because this is very good to do linear combinations with other spectra. But this is also probably won't get too much. Well, there are not so many sources. The emission lines can be variable, and but in principle, if you have enough of them, it would be good, I think.
Any questions online? Okay.
Oh, yes, there is a touch point that came in. Herbert, do you want to unmute and ask the question? Should I repeat it?
Can you hear me?
Yes.
Okay. Yeah, I was just wondering if, like, the common calibrators use the white dwarfs, 8 stars, G stars, provide enough spectral diversity for this reconstruction, or is it a wider, selection of spectra needed?
If you talk about stellar spectra, I think the most problematic part are the M-type stars. So because they have, with the spans, they are very variable, a very rich variety of shapes. And if they are not included, and you don't have very red sources included, this will be the most problematic thing. While I think, so B, O, B, A, F type might still be already well covered with the calibration spectra that are available currently. And I know it's a problem to get good calibrators of M-type because of various complications that come in there. But well, I also know that there are people already interested in having such calibrators, and I can fully support this idea of getting good M-type or K-type calibrators to get them to describe complicated spectra better and have more linear components in there. Don't do more white dwarfs. We have already so many white dwarfs.
Okay. More questions? You should be able. They should be able to.
I guess so. Usually, when you have measured photon fluxes, it's noisy, right? So you had a matrix equation there. Do you have any sort of comments or guarantees on how well conditioned that matrix is in general?
Yeah, this is again related to the problem how many basis functions you actually include in your case. In a perfect mathematical world, it would just be it's either linearly dependent or independent. So this is not a problem. In practice, it will just slowly go into independence with components, functional principal components getting less and less significant. And again, in a perfect physical world, you would just look at the residuals, which will get smaller and smaller if you add more and more basis functions. And if you have reliable errors on your photometric measurements, at some point, the residuals will become just too small to be realistic. And you know that you will start to overfit your data and you make a break. In practice, this doesn't work so nicely because this is a very small decrease. And what you observe in practice is that at some point, which usually is very abrupt from one to the next basis functions added to the set, you will not find a full solution anymore, which is smooth. And usually you want to well, you can assume that the overall passband is smooth. And you will just find that if you add one more basis function, you cannot get an orthogonal component that makes the sum smooth anymore. This is, in my opinion, the best indicator that you have reached a point where you pick up too much noise and you cannot get any meaningful result anymore. So when I would do this, I would just stop at the point until I can get a smooth overall solution for my total passband, adding the two components. And this works in practice quite well, I think.
Okay, I think we will, any more questions for Michael, grab them at lunch. And let's, thanks so much. That on. Now we're gonna play, can we get this right? So our next speaker is Carlos Allende. No, so that's him in the back. Yeah, I know you're friends. You're Jesus Maíz Apellanes. He's going to talk about calspec and guidance geometry, assuming I can. Oh, yeah, up we are. I want to go to the beginning. Start.
Yeah. You look like Julie Andrews.
I don't even sing, which is so you don't want singing. Okay, there you go.
Thank you. Can you hear me? Yeah. Good. Well, it's great to be back here 18 years after I left. And also, it's actually this is my second calibration, Falmeric calibration workshop. The past one was, was a long time ago in a galaxy far, in a country far away, which I have some memories here. Right, some of the people in the audience. Susanna is not looking.
I'm setting the time.
Yeah.
Oh my goodness, that was
anyway, yeah, so that was 18 years ago. For example, I learned in that conference that from Ralph, that when you're doing calibration, it's very important to keep your balance. Anyway, so this is a brief description of my talk. I'm going to go very fast to the first part because in this audience, most of you know about Gaia. So I'm going to be talking to them about what we did for the previous data release calibrations and what we have done just now. And this is a summary of Gaia. It's lots of information, but you know, so basically the idea in Gaia is that it releases lots and lots of information in data releases. We are now by data release 3. There will be 5, and there is lots of data. And what I'm going to be talking about there is in the basic data is a 3-band mean photometry. And this started happening in data release 1, and then in data release 2, and there is data release 3, and there is lots of other data, but you don't need to know about those. What does Gaia look like? But this, when I go to work every morning, I have basically a one-to-one model at ISAC, and here you see what it looks like. So it has this big sun shield, and then of course the spacecraft itself is in the back. And the important thing is the focal plane. This is the, in case you're not familiar, the peculiarity of Gaia is that it's taking data continuously, and actually the stars move like this. So it moves, this is what a star moves like in 10 seconds. So the chart is moved in the detector and then collected at the end of the detector. This has one of the nice features about this is that flats are much easier because basically you are detecting a star over many pixels in the detector. But the thing is that two important things. First, there is this sky mapper. These detectors in there are used to estimate the magnitude of a star, and depending on that, it sends a signal to the rest of the detectors, introducing, for example, electronic gates, meaning that bright stars and faint stars are detected in a different way. And this introduces electronic effects in the photometry that you have to account for. So in this part, in the astrometric field CCDs, is where you get not only the astrometry, but also the G band, right, which is the main photometric passband. And then you have the blue and the spread photometer CCDs, in which here you have a dispersing element. So you're basically doing objective prism spectroscopy. But when you get the BP and RP passbands are basically the collapse of that. So effectively it works just like a normal photometry, but you are actually spreading first the spectrum and then you are collecting all the photons. So when the first Gaia data release came out, I started looking at the data. By the way, in data release 1, there was only G-band photometry. And I realized something, that using calspec and other, the next generation spectral library, which is also done with STIS, as spectrophotometric standards, that there was a very strong color trend, meaning that when you compare the difference between the observed photometry and the synthetic photometry from Steve's data, and you plot it against color, this was Tycho color, you had a trend. This meant, obviously, that the nominal passband was incorrect, and there was a need to correct it. So I did a very simple, quick and dirty analysis, and I published this in this letter. And by just applying a simple transformation, I discovered that if you use a corrected passband that was redder than the nominal one, you got rid of that slope. Why did this happen? Well, this was actually kind of an expected effect knowing what had happened in the mission, which is that at the beginning of the mission, they had a water deposition on optical surfaces. So the real passband at the beginning of the mission was redder than expected. However, as time went by, the water basically, of course, started disappearing. And for the data releases, you get an average passband that becomes less and less contaminated. So the passband is expected to change with time. And indeed, that Gaia data release 2 came out. And at that time is when I teamed up with Michael with all this nice technique that he has explained to you. So we applied it for the first time, right? And in this case, for the 3 passbands, using this, as I said, more sophisticated analysis. And in this case, we use CalSpec plus other STS standards. And we found a number of things. First of all, that the passbands were different from, again, the official, even the nominal and what was at that time, the DR2 official calibration. And here you have examples. So what you have in red was the official calibration. And what you have in gray was our calibration. And you can see they are similar, but slightly different, right? This is the same effect for, that was G, this is RP. And in this case, there were, again, small differences. But the most important thing we discovered was this, which is that for the BP passband, there is an effect, there is a cut at 10.87 magnitudes, meaning bright stars and faint stars have a different passband. And using the techniques that Michael has explained, we discovered that if you look here, this is for the bright BP. You can see that between the red and the gray, there's a big significant difference here, which is that the real passband was much less efficient at the rest of the Balmer jump, which is around here, right? But if you go now to the faint stars, you can see the difference is not that large. Okay, so just to go back and forth, right? So there is really a difference. Why is this? Well, the reason for this is what I explained before, the use of electronic gates. So there is so what you have here plotted is what is the dispersion, the real, the sample standard deviation. That means what is the scatter in the, what is the scatter in the photometry as a function of magnitude for different colors. And you can see there is clearly a jump. It depends on the color, right? But it means that the photometry has a different behavior for faint and bright stars. But that, of course, if you don't include it, then it includes an additional scatter. But if you are able to include it, then you reduce the scatter in your comparison between the spectrophotometry and the photometry. And when we did this is, so with this, we were able to do an absolute calibration. So this is everything what we're talking about all this week, of the order of between 8 to 10 millimagnitudes. So let's 1%, right? Okay. Now here comes the early data release 3. So at this point, we want to do our analysis, but we discovered that one of the basic problems is what Michael was telling you about in the last talk, is that we had a problem in that we didn't have stars that were red enough. So this was when you were reconstructing the passband, this was introducing effects, another termination. So we wanted to get out, so all this nasty orthogonal component, we wanted to make it as unimportant as possible. And in order to do that, you need to include more red stars. And for that, we had this problem. So you see, this is the distribution and magnitude of what is the Gaia sample. And you can see that these, which are red stars, there's plenty of them. A large fraction of many stars, for example, are here, which are red clump stars, and they are extinguished. So they are very red. And even in our previous calibration, we only had 3 stars in the range between BP minus RP of 2.9 and 4.8 is range, right? But 0 to the left, to right. So what we did is we proposed an HST program with Ralph and Susanna, and we to observe very red stars, add them to CalSpec, and recalibrate both DR2 and DDR3. So now instead of in this range, we have 5, but now we have 4 that are very red. This is in a histogram. And by the way, we submitted this to AstroPH a couple of months ago. And this is the preliminary version of the final analysis, which is a paper we'll publish next year. So what you're having, this is a logarithmic histogram. What you have in green is the observed distribution of Gaia colors. And traditional calibrations use only this type of stars. But now we have these stars here, which are very red. And these had never been used for optical calibration before. But they are stable, and they can be used as calibrators. Most of them are extinguished red clamp stars, okay, which are very photometrically stable. And so using that, we were able to reconstruct the passbands for both DR2 and DR3. And this is the big summary of what we found. So not only did we do EDR3, but we did DR2 again, because now we have a better calibrators. So first thing, we have really a 6-filter system. So we have G plus B, P plus RP, but for DR2 and DR3. The passbands are slightly different from the other releases. Why? Again, factor number 1, what I mentioned before, the fact that the water deposition is changing on average. And second, that each data release is basically all the data are put into a computer and they are processed together, and the analysis is simply different. Okay, so that's the first thing. Second, remember that for DR2, for BP, we had to divide in 2 wavelength ranges, right? Okay, so now with the new analysis, we have, of those 6 bands, we have 4 to divide in 2 ranges. The 3 passbands in DR2, G2, BP2, DRP2, and G3. Okay, so that's second effect. Third effect, there are magnitude corrections needed in 2 cases, G2 and G3. This was not known before, but for G2 at least, not so much for G3. So when you get from the catalog and you want to compare to spectrophotometry, you have to apply these corrections. But when you do all of that, finally you get what are the comparisons between, what are the dispersions between, and the comparisons between spectrophotometry and photometry. They have gone down significantly. They are now, you see, for DR2 between 4.5 and 8.7, but for DR3 between 3.4 and 5.7. And indeed, if you compare for faint stars, which are what most people are interested in, you have 3.4, 4.0, 3.9. So now, the cross-calibration between CalSpec and Gaia is of the order of 4 millimagnitudes. How much of this is CalSpec and how much of this is Gaia? Okay, if you remember Ralph's talk from yesterday, the value he was giving was about 1%. But if you actually look in the optical, meaning between the Paschen and the Balmer jumps, the value there in his plots is much lower. It's like 0.1%, so 1 millimagnitude. So most of this, I suspect, is actually Gaia. So that's our lack of knowledge of the Gaia passbands, if you want. But again, we can go to out of the order of 4 millimagnitudes. So just to go quickly, so these are the corrections. So these are the type of corrections you have to apply when you retrieve the data from the catalog and you want to go to the real values. You have to apply this for G2 and G3. This is how you compare the G passbands for bright and faint and for DR2 and DR3. And the important thing to look there is if you compare the yellow and green against the other 2, that's the difference between DR2 and DR3. You can see that the passbands have become bluer. So this is going back to nominal, right? So it was too red because of the water deposition. Now it's going back to nominal. The effect of this is that if you I compare this with an independent sample of OB stars, and I compare the color against the difference between the G3 and G minus G2. So if you do this with spectrophotometry, you expect simple curves like that. If you don't apply the magnitude corrections, you get something that is red. So it's not so much a good agreement. But once you apply the corrections, you get something that is very tight, meaning that those corrections really improve the photometry. RP, when you do RP, and now compare the EDR3 with the the green one, which are the faint ones. And you can see there is a significant difference. This means that if you do RP2 minus RP3, you get a color. So there is astrophysical information in there. But even more important, where you have a lot of astrophysical information is when you do it with B. And especially if you compare the green and the magenta, that's the difference between DR2 and DDR3 for faint stars. So there is a big there's a difference in how sensitive it is to the left of the Balmer jump. So you can use this, and we actually use this. So here, you have this effect. So this is a comparison between BP R minus 2. So the red and magenta points are for bright stars, where the two passbands are very similar, so you see it's mostly flat. But when you compare it for the faint stars, there is a significant difference. And indeed, if you do this now with the stars of different colors that are all faint, you can see blue stars there are O stars, green are B and subdwarfs, and the red ones are A and F stars. So you can see that there is a trend. So you can use, in a sense, BP DR3 minus BP DR2 to get a measurement of the Balmer jump, just from photometry, no spectrophotometry included. So this is kind of, the famous old diagram by Johnson and Morgan in the 1950s using U minus V, B minus V. I mean, it's not to that point, but it's the same idea. And this is my song.
Thank you. Questions? Questions online? Carlos?
Can you use the same methodology to recover the response function for the XP, for the spectrophotometry from Gaia?
That is a very different, as Michael was explaining in the previous talk, that's a related problem, but it's slightly different. So the math behind it is similar, but it's not exactly the same. So that means, so the problems in there are, so you have a sensitivity problem, which is the same one, but you have the problem with the line spread function, which is what Michael was saying before. And the reason for that is because when you do this, so the problem here is that this is a sensitivity for the photometry, but for the spectrophotometry, eventually is similar. And what you have here is this big drop. So once you have this big drop, you have the problem that the spectra, the flux from flux at this wavelength is contaminating the one at lower wavelengths. And that's because of the line spread function. So that requires different techniques, which is you actually have to work on this set of bases that Michael was explaining.
Carl, Joe, and Eli.
All right, I have probably a very simple question. I had imagined that DR3 included all the data the guy had ever taken. Is that correct?
Okay.
Or only the data between DR2 and DR3?
No, it keeps increasing. So basically it was 1, 2, and 3 years.
Yeah, but the DR3 includes years 1 through 3.
Mm-hmm.
So I guess I'm a little confused on how the DR3, you're getting a single passband function for DR3, even though it includes an evolving passband function over time. Can you comment on that?
Yeah, that's because everything is processed together. So in the processing, it's assumed that you have a single passband over all the time, but that is not true. So what you get is an average value. And when you get the final data release, basically, so the effect of the water position lasted for, I don't know, maybe 6 months or a year, right? So in the end, when you get the full 10 years, the effect is, my prediction is that in the end, the bandpass will be very close to the nominal one. But it will be an average one.
Okay.
Joe?
So if I understand correctly, water deposition on somewhere in the optical train causes some shifts of the bandpass in this visible spectral range. This would seem to be something that could be verified in a laboratory by actually depositing water on optics and seeing. Has anyone ever done this? Have you looked at the literature? Is anything independently could confirm your hypothesis?
Okay, So to make this clear, so there is a, so I'm not part of DPAC, right? So DPAC is the official consortium that processes the data. So I'm kind of an independent contractor, if you want. And somebody will describe me as a pain in the ass. So actually, that's not my job. That's their job.
So the answer is no.
No, I haven't done it. No.
That's all I wanted.
Okay.
SDSS did this. SDSS took out the filters and remeasured it, and then filter is rule shifted, actually. It's opposite of yours.
Well, I mean, that's what the data is saying. So that's why they say, I mean, and this, and by the way, so just to clarify, so there are, if you read the literature, there are other people who have done similar analysis, right? So especially for DR2, this happened. And we basically, we got small disagreements on the smaller details, but not on the basic effect. So if you look at the other passbands from all the other people did for DR2, they found the same effect.
Question online.
Okay.
Can you mute and ask? Or I could read it.
Oh, would you like me to ask directly?
Yeah, go ahead.
Okay, so I said, I guess these are all effective passbands. Do you think something like changing the PSF and hence the color dependent or magnitude dependent aperture correction can play a role in the changes in effective passbands?
Okay, so this is a different question, and that is it relates to how Gaia works, which is very different from anything else that is done from the ground. So all the processing is done on board. Okay, so that's a hypothetical question, but it has no answer whatsoever, because all the data is processed on board and sent to Earth. And the people at the Gaia DPAC work a lot on this, and they model the PSF and they do all those things. But all of that is done before you get the official photometry. And if you go into the Gaia, in the DR2 and the DR3 papers, they have lengthy discussions about how they did this, but I haven't gone into anything like it. This is, again, all this is processing based. So the sources of information are the catalogs that come out of the data releases. And then what we do is we process the HST, well, I mean, some of the HST data. So Ralph, for example, did the extraction for the spectra and then all the CalSpec. So what we do is that, and those are our input bases, and then we compare it. But we don't go at all into trying to model that, among other reasons, because it's just way too difficult, and basically we don't have the means to do it.
Yeah, so that's what I meant with effective passbands. Really, we don't know if it's really the filter, the passbands or any that are changing. It could be something else.
Okay, I think we have time for one more question. Too many people asking questions.
So Eli.
Eli had his hand up. He was next in the queue. So.
Could I project here? Let's make it quick. So I don't understand this plot. That's which is related to the previous question. I don't understand how DR2 fainter could have such, sensitivity at 3500 that would then go away in some sense. So is it a systematic from something like, PSF blending or?
No, this is most likely an electronic effect. So the point is that, remember what I showed you about oops, let me go this way. So this is how Gaia works. Okay, so stars are detected here, okay, as they enter the detector, and they have an estimate of what is the magnitude, and depending on that, the data is processed electronically different, right?
But why would it change from DR2 to DR3? Where does 50% of the 3500 go?
Again, okay, so that depends on how the electronics work and everything. So it's indeed, of course, it's a black box. So what we're just reporting is what is the result. So if you don't do this, basically what you get is that the dispersion in the photometry clearly increases. And the reason why we show that this is not, we're not making it up. And by the way, this is just one of the plots. There are many of these. The fact that here you do see the effect. So there is a jump at that magnitude. And that's the dispersion. So there is something that makes the dispersion increase and with a dependence on color as you go at one point and the other of the magnitude range.
Okay, I'm going to let Michael answer this question.
Yeah, let me just make a comment on this now as a DPAC member again. The passbands you are seeing here are not necessarily physical passbands. The data that is collected is put together and it just made sure that all the observations converge to the same photometric system, but there's nothing that is implying that this photometric system is anywhere a physical system on this CCD in the field of view or somewhere. So it's somehow artificial, which means it can change from data release to data release in some degree, and it does not have to be a physical one. So if you have a change somewhere, it might just be that the system has converged to another photometric system independently of what has actually happened physically. So the differences between the different magnitude regimes are clearly related to electronic effects, but the overall passband does not have to be any passband somewhere inside the instrument.
Okay, and on that note, I'm going to close this so that we can go to lunch. If you have any more burning questions on the details of, have lunch with Ashish and Michael. Again, I want patience and being flexible. We struggle through our technology.
The schedule says group photo.
Oh, when's the group photo? Tomorrow.
It's a telepathic schedule.
Okay.
Yes.